the two things: to detect the outliers and reconstruct the data as well. And when we have more complete data, we can make better predictions. So that's the goal of this research. Now, to do that, there are a number of methods in the literature that are focusing on different aspects of performing this detection and reconstruction. Most importantly, the latest algorithms are categorized as the hybrid algorithm, which I am working on as well. By hybrid, it means that I'm trying to utilize the temporal information as well as the spatial information, like information from today as well as information from the yesterday and the day before yesterday, and then maybe information from the future as well, or information from previous years on the same day, right? So in trying to utilize the temporal information and also trying to utilize the information of today at different times. Like if I have missing data at 1 p.m. and I have data at 12 p.m. and 2 p.m. and 3 p.m., then I can try to use that data as well to accumulate to complement that missing data. So this is all about temporal and spatial information that can be used to detect missing data and reconstruct, and which is I am doing. And also the data fusion from multiple satellite is also an important factor that can be done. It's a very crucial task of fusion data, because but it means that when you have the input data, you can have data from multiple satellites. Like if for day one I have data from a satellite X, and then for day two I do not have data from the satellite X. So what I'll do is I'll use the data from a satellite Y for the same day and same location. And in this way, I'll be using data from multiple satellites, which will, of course, in turn make a concept of data fusion. And this is all is what I am doing in this paper. The model flows start with the input data, and then the second stage is outlier detection. And once detected, we move on to the reconstruction of the missing data. And then finally, we have the improved image. So the important thing here is to understand the study area, the data, before we move further from in this for the model. Now, the data is freely available on NASA's website. I'm using MODIS satellite. MODIS stand for Moderate Resolution Imaging Spectroradiometer. So the raw data is downloaded from the website, from NASA's website. The MODIS is one of the satellite. And this is then processed in ArcGIS or QGIS, Geographical Information System data processing tools. These are some of the tools that I have used. And then raw data is processed, as you can see an image on the right. So this is something that you get when you have processed a raw data. Now this image is basically a region in China, the Beijing Tianjin Hubei region, BTH region, that I have chosen for this study. So the satellite data for this region is downloaded, the land surface temperature data. Now, I have used images from 1st of January 2018 to 5th of January, these 5 images, 5 continuous days, for 2 of the MODIS product. One is MYD and the other is MOD. So MYD11A1 and MOD11A1. So these two MODIS products are actually capturing data at a different time. Like MYD11 captures data twice a day, 1:30 a.m. and then 1:30 p.m. And similarly, MOD11A1 captures data at 10:30 a.m. and p.m. So these two products I am using. So this is these two products, and then 5 images from these 2 products. So I'm trying to create a manual data fusion as well. So I'm basically feeding the input stream to the model, or the input images to the model that are from these 2 images to complement the outlier detection and then reconstruction. So these are the images. Now the yellow A region, as you can see here, are the missing area or the outliers. As you can see, that there is a lot of missing information, and the accuracy of the algorithms is challenged when you're trying to make prediction or detection of outliers for a very larger region, right? So I'm trying to I have experimented on different size of different regions, and I'll share the results as well, which is definitely affecting when you're trying to make the detection, outlier detection and reconstruction for a very larger area. So from A, B, C, D, and E are basically the 5-day images of the land surface temperature for the BTH region. Now, the model starts with outlier detection. To do that, the program runs and you have to select a region of interest in which you want to detect the outliers and reconstruct, right? So an M cross N window with the drag of the mouse, you're going to select the region in which there are outliers that you want to detect and reconstruct. Once you do that, for all those 5 images, a slice is created. You can see a mosaic sort of an image, or a stack of images is created. So this is the region of interest for the, like, blue one is the region of interest for one image, and the green one is the region of interest for the other image. So on the same area that we have chosen, all the other images are sliced in for that same region as well. As you can see here, that this square box here, I'm trying to choose a smaller region here, and you can see the yellow regions, the yellow values, these are the outliers or the missing values. So all the images, this particular slice on the same location will be captured for further processing and detection of outliers. So I'm using dynamic time warping to do that. Now, dynamic time warping is used to measure the similarity between 2 temporal sequences. And now I'm using that to measure the similarity between the pixels. Now, that the output is in the form of a distance. So as the graph on your right, as you see, is obtained for the experimentation, and the very high spike in the distance value means that the images or the pixels are very different. Like temperature from today and tomorrow, it's not a sudden increase or it's not a sudden decrease, right? It's a sort of a linear increase or decrease. So this cannot be so this must be an outlier. And then there are smaller differences of temperature, so smaller changes of distances, as is quite visible in the graph. So different pixel locations and different distance values, right? So I'm now dynamic time warping, as you can see here, image I and I+1. So 2 consecutive images are compared, or image slices that we took in the previous step are, and each pixel of those image slices is compared with each subsequent image slice. Like slice 1 is compared with slice 2. Each pixel of slide 2 is then compared with the slice 3, each pixel of slice 3, and then each pixel of slice 3 is compared with each pixel of slice 4, and this would give us a series of distance values, right? Now, quite visible that whenever there is a huge distance, a difference of distance, it means that there is some malicious values or anomalous values. These very high distances are actually indicating the anomalies. So a threshold is set. Now this threshold I'm currently obtaining by experimentation and by comparing known pixels, like a known true pixel and a known outlier, to see that what sort of distance value I can get if I am comparing known pixel and an outlier. So this threshold is I am currently getting in this way. And when I apply this threshold on the distance values that I am getting, uh, I'm getting I'm storing 2 things here: the coordinates, like the location of the pixel, and and the list D is basically showing me the distance of the at that location, like at coordinate XY, the distance is 20 at coordinate x1, y1, distance is 30. So each pixel is compared, their coordinates and their distances are saved. So when I apply the threshold, I'll have a filtered list of pixels whose distances are very high, or greater than or equal to the threshold. So these list of pixels with their location will be the outliers, right? So now when the threshold is applied, I have the coordinates of outliers and the distances as well, which are telling me that this is how these much are the outliers in this particular area. Now, coming towards the missing data reconstruction, now, because I have a list of coordinates and their distance values, which are the potential outliers. And if you can imagine here, like consider this black dot here is an outlier. Now, the subsequent slice at the same location of this black dot, and then for the orange and this one, and so this is sort of a series, distance series. So what I do is the algorithm finds a distance at which is a minimum value, like at the location of this outlier, this black dot outlier, in this whole series of images. It tries to find the minimum distance, like minimum distance at the same location in other images. And when we have find the minimum distance, now that minimum distance is that pixel which is at the minimum distance in the locations, corresponding location of the outliers, is taken as the corresponding pixel or the reference pixel PCD. Now, considering that I have found reference pixel in one of the other image slice, I'll take that reference pixel and compare it with other pixel which are in the 3x3 window of the outlier, right? So once we have found the reference pixel, we'll take a 3x3 window around the outlier location. So now, as you can see that the reference pixel is sort of a temporal information, right? So in this way, I'm utilizing the temporal information. And now this 3x3 window around the location of the outlier is spatial information, which I am now utilizing to do the reconstruction. So what the algorithm does is basically compares the reference pixel with the surrounding pixels of the outlier, and whatever pixel is at the least distance in the surrounding of the outlier, it takes that value, copies it, and placed it at the location of the outlier. So basically it is now trying to complete that temporal series from image 1, 2, 3, 4, and the missing data in image 4 is now complemented with the temporal information or the surrounding information, right? So if the information is missing in this particular area, I'm using the information from a nearer area, another area in the image, to complement that, to complete that. And for to do that, I'm using the temporal information in another image to find the most suitable pixel value, right? And this is all about the reconstruction of missing data. Now, some of the results are here. Sometimes there are exact matches, sometimes there are non-matches as well, of course. Like the window size of 4 by 4, if the window size, like the region of interest I have chosen is 4 by 4, like number of outliers are 5 in that. So one pixel was the exactly is the same that that was replaced, and there were 5 non-matches. Like it was the random outliers that were introduced, it was not exactly the same, but it was closest to it. So this is basically this shows the working of the algorithm. And as we increase the size of the region that have outliers and that we want to reconstruct, number of outliers increase, and the number of matches and non-matches also keeps on increasing. So 21 for the largest window of 15 by 15, 62 outliers were introduced, and out of those 62, 22 were replaced exactly the same, and 41 were slightly different, but these were from the surrounding areas, so that would mean that these are potentially uh, closer to the actual values, not the exact values, but closer to the actual values. Some of the results here are in the form of a pair in the images, as we see the outlier in the top row here, and then in the bottom row, these are the reconstructed images. And now, once these images are reconstructed, I'm trying to get the average distance between the original and the reconstructed value to see that how much accurate is the value. And it is quite evident that as the number of outliers increase, or the number of or the area with a lot of missing values increase, the reconstruction tends to basically underperform, right? So this is something that needs to be addressed, and is part of my future work as well, because currently I'm trying to utilize, I'm simply copying and pasting the values of the pixel, but to do that I'm using the temporal and utilizing the temporal and spatial information. The next step of this research is to, instead of copying the pixel values, trying to estimate the pixel values using deep learning. And this is what I'm currently working on to improve this research further. Thank you very much, everyone.